Got there in the end. The obligatory disclaimer. So just firstly, what are the rare earths? Well, I'm sure we're all familiar that they consist of the 15 lanthanides at the bottom of the periodic table, but they also include scandium and yttrium. And as such, they're all metals, but they're not particularly rare. So cerium is the 25th most abundant in the crust, while lutetium, which is the scarcest rare earth, is the 60th most abundant. A common theme throughout this presentation will be a focus on what we refer to as the magnet rare earths, and they're highlighted there in red. So praseodymium and neodymium represent part of the light rare earths, and then we've got terbium and dysprosium, which represent part of the heavy rare earths. And in terms of grades with these deposits, it's commonly expressed as a function of its rare earth oxide, or TRIO, which stands for trace rare earth element oxide. And essentially that includes all the lanthanides less promethium. So promethium doesn't really exist in nature. I believe it's formed in fission reactions. So it consists of those 15 lanthanides, and it may or may not include yttrium, and it may or may not include scandium. So where do we find these rare earths? Well, pretty much in almost any piece of modern technology. So lighter flint, something as mundane as lighter flint, has a swath of rare earths within it. Catalytic converters largely uses cerium to convert carbon monoxide into carbon dioxide and water vapour. There's a big application for it in ceramics and glass manufacture. And when you pop into your car tonight, you know, just think of your windshields and your mirrors there, which will be polished with cerium oxide. But the bulk of the rare earth market today really revolves around permanent magnets in electric motors. And you can see the composition there of those magnets. So 60 to 70% iron, 1% boron, and somewhere between 27 to 37% neodymium and praseodymium. And then for high temperature applications, you have about 2% terbium and dysprosium. So we'll see these permanent magnets in your common white-hot house goods, lifts or elevator shafts, automated robotic lines for car assembly, even in medical applications such as MRI machines. There's a large military application, and if you can believe anything you research on the internet, the F-35 fighter jet is suggested to have a payload of something like 430 kilos of rare earths. And we increasingly see them in electric vehicles and offshore wind turbines. So growth in the permanent magnets, it is largely driven by electric vehicles and offshore wind turbines, with EV sales predicted to double by 2029 and new wind installations forecast to grow. So I think that's offshore wind installations forecast to grow 17-fold over the next decade. So that's led the US Department of Energy to classify these magnet rare earths as critical in terms of their short to medium term supply risk and importance to energy. And that's why we're pretty bullish about exploring for it, I guess. So just very briefly to have a quick look at the different deposit types. There's really, this can be subdivided very broadly speaking into two different types. They're either primary or secondary. So your primary deposits consist of your hard rock deposits such as carbonatites and alkaline igneous deposits. So an example of an active carbonatite mine is Mount Weld in Western Australia, shown there in the bottom left. And essentially they're mining the enriched laterite position on top of that carbonatite. These primary deposits, they're high grade, so your alkaline igneous deposits such as Toongai, which was mentioned before, typically have TRIO grades above 0.5%. And then the carbonatites, such as Mount Weld here, will have in excess of 5% TRIO. And the rare earths are largely driven by magmatic to hydrothermal processes. In comparison to the secondary deposits, which are clay-hosted deposits, they're a heck of a lot lower grade, so ore grade can be somewhere above 500 ppm TRIO. And the rare earths are exchanged or adsorbed onto clay minerals such as kaolinite, so they essentially hang off the clay minerals as weak ionic bonds. And of course, the primary and secondary deposits, they're mined in different ways. So for the primary deposits, it would employ traditional drill and blast and open pit mining. And because the rare earths are found in resistant minerals like monazite and fluorocarbonates, which is besnazite, it requires huge acid consumption at pHs of less than 1 and high temperatures to extract or to liberate the rare earths. And this is in comparison to the secondary deposits, which can employ shallow strip mining or free digging. And an example of that is in the bottom right-hand images, and that's from AR3's trial mining of copper Mara in southern South Australia. So the rare earths are liberated in these secondary deposits from clays using somewhere between 0.3 to 0.5 molar ammonium sulfate at a pH of 4 to 5 for 30 minutes at ambient temperatures. And I think it was best described in the Money of Mines podcast recently, where they drew on the analogy of going to Bunnings with a washing machine, buy some fertiliser, throw it in there with your rare earth clays and a bit of water, agitate it for 30 minutes, and you end up producing or liberating your rare earth. So somewhat of the simplistic analogy, but you sort of get the idea of the simple downstream processing to produce what we refer to as an MREC, which is a mixed rare earth carbonate, and that's what's ultimately sold to the market. So these secondary deposits, in the literature they're referred to as iron absorption deposits or IAD deposits. Other names you might see are iron absorption clays, ionic clays, and laterite hosted rare earth deposits. As far as I can tell, they all largely mean the same thing. And of course they're dominantly found in southern or southeastern China, which I've shown there in the blue polygon, and they account for about 80% of the global heavy rare earth market. So China really does have a monopoly on the heavy rare earths. However, there are some bigger deposits which are hopefully coming online. We've got Serra Verde there in Brazil, nearly 1 billion tonnes at 1200 ppm trio, and perhaps the poster child for these clay-hosted deposits is Meteoric's Caldeira project in Brazil, so 619 million tonnes at a little over 0.25% trio. And then, of course, we've got some homegrown examples here in Australia. I would contend that Narrabri is a variety, if you like, of an IAD deposit. I've already mentioned copper Mara in southern South Australia there, and deep leads in Tasmania would be another example. Just very quickly, looking at the formation principles of these IAD deposits, it essentially revolves around the lateritic weathering of an underlying fertile rare earth host rock, such as these peralkaline granites, which were discussed previous, felsic volcanics or cyanites, and they're typically formed in temperate to tropical climates. So I've included this type strip profile log, if you like, from the Zhudong deposit in China, which is said to be the biggest heavy rare earth deposit in the world. But essentially you've got this A-type granite feature there at the bottom of the profile. In terms of enrichment, it's about 2 to 2.5 times background trio, and essentially you have acidic soil water which will decompose this A-type granite, and that releases rare earth 3+ cations into solution. So these rare earth 3+ cations, they'll move down through the weathering profile, and essentially as the pH increases, the rare earths, or these cations, are exchanged or physically absorbed onto the surface of negatively charged clay particles such as kaolinite. So on this image here, that'll be represented by the ore body, and it's also referred to as the rare earth accumulation zone. So in the case of Zhudong here, that's about 1055 ppm trio is the grade of their ore body. Importantly, cerium's got, I guess, a couple of important diagnostic features within these systems, and that is because in that leach zone in the upper part of the profile, and when we say leached, it's leached from the rare earth 3+ cations, but in that upper leach zone, cerium 3+ will oxidise to cerium 4+ and form serenite. And an example there where it says cerium enrichment, that's the chondrite normalised plot as a result of that. And conversely, within the ore body, we also see cerium depletion. And perhaps the final point to make there is the ion exchange capacity of these systems. So that is where the rare earth 3+ cations adhere onto the negatively charged clay particles, typically represent somewhere above 50% of the rare earth mineralisation, and at Zhudong it's about 65%, meaning that I guess the other rare earths are caught up in secondary minerals and aren't all ionic in nature. All right, so let's start talking about our project now. It's called the Narrabri Rare Earth Project. We're located 340 kilometres west of Sydney and 12 kilometres north of the little township of Temora. Our exploration ground, it comprises 4 exploration licences for a little over 500 square kilometres, and it's held 100% by Godolphin or GRL. And the area in red there is our inferred resource, which is 94.6 million tonnes at 739 ppm trio, and that does include yttrium. And we've also got a 20 million tonne higher grade core within that. So just by way of a very brief regional geological snapshot, and in case I forget, our Narrabri deposit is highlighted there in the yellow star. But essentially the oldest rocks in our area lie west of the deposit, and actually west of that Gilmore fault zone, which is that north-northwest striking fault. So west of that we have the Lake Cow Arc volcanic complex, Ordovician age, obviously further to the north that hosts the Lake Cow gold mine, and immediately west of our deposit we have the Gidgenbung epithermal gold deposit, which is under care and maintenance. And essentially as that Ordovician arc migrates east over time during the Siluro-Devonian, it leads to extension, basinal development and seafloor sedimentation. And then through, I guess, ongoing extension leads to the emplacement of the Narrabri granitic complex, which I've simplified there as the dotted yellow outline. So this granitic complex, it postdates arc magmatism by about 75 megaanna or million years. And importantly, it's been divided based on its alkali content. And Suite 3, which, as we've already heard about, these A-type per-alkaline granites, it's featured on the map there as that dotted pink beige unit. That underlies our deposit. And as you've already heard, they're a fantastic exploration target vector. And just to rehash, it's because they're enriched in these high field strength elements like zirconium, niobium and tantalum, and they're also enriched in other rare earth minerals such as monazite and xanthine. In terms of our deposit history, pre-1999 very little work was done. The granites weren't really deemed prospective for much. And then in the late 90s up to 2016, a company called Capital Mining pegged the ground, and they were basically chasing that pegmatite that you can see on the screen. However, they soon realised that these per-alkaline granites were naturally enriched in zirconium, and they probably had a Toongai type model in the back of their mind. And they drilled a series of holes shown in the blue and the black dots there, and they released that zirconium resource on the screen. Fast forward to 2022, Godolphin entered into a joint venture with a private company called EX9. We now own the project outright, but essentially we approached this project from a rare earth focus, not from a zirconium focus. And we drilled those 31 diamond drill holes for, as shown there in the green, for a little under 1,400 metres in 2022, and we've released that JORC resource there, which is that 94.6 million tonnes at 739 ppm trio. So, really for a 100 million tonne resource, or getting close to that, it's a very little amount of drilling really that's gone into it, 65 holes for under 3,000 metres. Okay, in terms of our deposit dimensions on this grade contour map on the right hand side, we're about 2.6 kilometres from south to north and 1.8 kilometres from east to west. We're open to the north, we're open to the south, and we're open to the west, but we're largely confined by the Narrabri Hills to the east. Now, mineralisation, it's hosted in saprolitic clays, which is positioned directly on top of this per-alkaline Narrabri granite. And in the cross-section there, that per-alkaline granite is represented as the red, which is our bedrock, and our rare earth accumulation zone is essentially the yellow and the orange. So in the east, the mineralisation is essentially at surface or very close to surface, and it gently dips back to the west, where in about the middle of the deposit, the rare earth mineralisation is approximately 47 metres below surface. And that rare earth accumulation zone proper, which is the orange unit there, is somewhere between 10 to 25 metres thick. Just to give you an idea of what it looks like in this 3D perspective view, you can see there the Narrabri Hills off to the east, which confine the resource. The Godolphin drill holes are shown there as the black dots. And the resource essentially extends from those hills out to the west where it meets that north-south road. That's about 1.8 kilometres. The other important thing to note here is just that very weak bowl shape between the road and the Narrabri Hills. Obviously forms some sort of weathering trap to promote the decomposition of the granite. We get asked this question a lot, what's our mag-Rio makeup? It's really because all the value for the rare earths comes from these four elements. So for us, as a function of trioless cerium oxide, our mag-Rios account for 26% of the resource. If it's just as a function of trio, which for us includes yttrium, it's somewhere around 18 to 19%. And you can see there that we're heavily weighted to the light magnets, being neodymium and praseodymium, so they account for roughly 3/4 of our mag-Rios. But the real high value dysprosium and terbium represent about 24% of the mag-Rios. So just to give you an idea of what a typical profile looks like through the deposit, so this is taken from the first drill hole that Godolphin drilled, a diamond drill hole. In the upper 27 metres, we have what I refer to as our upper leach zone. So it's grading about 188 ppm trio, so pretty much right on background. And tile 15 there shows that it consists of these completely weathered and mottled red, white, brown saprolitic clays. And importantly, we see cerium enrichment as a function of that chondrite normalised plot, which again is one of these diagnostic features of these IOD systems. As we migrate further down the profile between 27 and 55 metres, we enter into this, what I've called a partial leach zone, but it's essentially the start of our rare earth mineralisation. So we've got nearly 20 metres there at 537 ppm trio, and the top of that horizon actually starts on the pisolithic saprolitic clay horizon, which you can see there at tile 28. Sitting directly underneath this is our rare earth accumulation zone. So we've got 9-10 metres at 1075 ppm trio, and that's hosted in these purple, white, brown clays transitioning into sap rock. So we do have some weak to moderately weathered granite at the base of that horizon. And then underneath that, so in tile 66, that's our per-alkaline granite. You know, about 4 to 5 times background trio enrichment, so it is quite an enriched rock. And the composition there, 60% alkali feldspar, 36% quartz, 3 to 4% sodium amphibole, and then we have traces of zircon, monazite, fluorite and ilmenite. We've been lucky enough that the Geological Survey of New South Wales has high-logged our holes for us, and we're just looking at a snapshot of that data from hole 1. And really what I'm trying to show here is just that our dominant clay mineral in that saprolitic horizon is kaolinite. It obviously overlaps with our rare earth accumulation zone. And then you can see there plagioclase starting to increase, signifying that we're starting transition into the per-alkaline granite. And we also see niobium increase near that basal contact, if you like, and it's also relatively enriched in rubidium. So in terms of our rare earth mineralogy, I've already mentioned that kaolinite is our dominant clay, but we also see some smectite in the system. And our rare earths, they're either adsorbed directly onto these clays, or more dominantly they're found in 2 secondary minerals. And they are neodymium lanthanite, which as the name suggests is neodymium and lanthanum. It's actually a carbonate. And then we've got cerite, which consists of cerium and lanthanum. And then we also see some other rare earths in trace amounts, monazite, xenotime, and we've got some other unknown microcrystalline rare earths, and they potentially host some of our magnet rare earths. Diagnostic metallurgical test work, I really can't emphasise enough how important this is in these deposits. It can really make or break your project. So if you're ever out there reviewing it, do this sooner rather than later. For us, under typical desorption conditions, so that's the washing machine analogy, we achieve extractions of up to 17% trio, indicating that only a small part of our deposit is truly ionic in nature. And our remaining rare earths are dissolved using a lower pH acid. So we still use ammonium sulfate, but we use additions of sulfuric acid to maintain a pH of somewhere between 2 to 2.2. And by doing this, we've achieved really high recovery rates of up to 95% of those 4 magnet rare earths. And this is largely attributed to the partial encapsulation of the rare earth bearing secondary minerals, which are either found on the edges of kaolinite grains or other grains such as K feldspar and quartz. This is probably easiest to describe on the image on the right hand side there. So we've got an angular grey quartz fragment. The areas in white represent our rare earth mineralisation. And at the very southern margin of that quartz grain, we've got neodymium lanthanide and xenotime. So really, it's the pH of between 2 to 2.2, which is attacking that part of that quartz grain, and that's what we're liberating. And it's really on that basis that we've persevered with the project. We're certainly not chasing that 17% ionic component of our deposit. Just in terms of our exploration upside, we've been lucky enough that the Forbes Airborne EM survey, which was flown through the Geol survey and also Geoscience Australia, overlapped with the entirety of our project. So we've got something like 13 or 14 flight lines covering our tenement package. We've reprocessed that data, and in particular I'm just showing you here line 31020, which directly cuts through our deposit. So that section that you're looking at there, it's a conductivity depth slice image. MIZOW Geophysics did the reprocessing for us. But essentially what you're looking at there, the reds represent something conductive, which is more than likely our clays, and then the blue represents resistive basement. And then on the right hand side, and it might be a little bit hard to see, but we've actually overlapped where our rare earth deposit sits, and that's on basically on the boundary, the southern margin, bottom margin of that conductivity feature. And importantly, we think we can trace that horizon out to the west for another 1.5 kilometres, and we've never drilled out there. So it stands to reason if there's a per-alkaline granite position underneath that untested area, you'd expect to see a rare earth accumulation zone in the regolith profile. So just in summary, the Narrabri rare earth mineralisation, it's hosted in saprolitic clays and weathered bedrock, and we're positioned directly above a per-alkaline granite. We see a similar regolith profile to other IOD deposits. Notably, we have serum enrichment in that upper leach zone and depletion in the rare earth accumulation zone. But given that only 17% of our deposit is truly ionic in nature, and we require a pH of between 2 to 2.2 to leach the rare earths from those other secondary minerals or K-spar or quartz grains, I think it's probably more appropriate to classify ourselves as a hybrid IAD deposit. We're currently undertaking a scoping study with Ausenco to determine the profitability of extracting rare earths using ammonium sulfate and sulfuric acid. And you know, if we get into a positive outcome, then I think it stands to reason that there's a fair amount of exploration upside there. So thank you for your time.